Okay, so hopefully this is the last video, and this is about phase diagrams. And so let's talk about phase diagrams. They're a plot of pressure, and units can be anything, but we're just going to use atmospheres here, versus temperature and degrees Celsius. So if we look at a phase diagram, we have this little curved line here, and we have a negative slope here that extends that way, and then we have this other curved line that ends in a point. Oh, and I should say this is for water, specifically for water. Every substance has its own phase diagram. Now let's talk about the phases in those phase diagrams. At low temperature, you would expect something to be solid, liquid, or gas. You'd expect it to be a solid, right? High temperature but low pressure, we would expect it to be a gas. And then that only leaves us with one choice. Higher pressures, higher temperatures, though, is where the liquids are. Okay. And then this little point right here, where all three of these lines come together, this is called the triple point. Okay, and there's a specific temperature for that. But at that temperature and pressure, I'm sure there's a specific temperature and pressure, but at the triple point, all three phases are in equilibrium. That might not sound very interesting to you, but I'll try and post a video of this. You can literally see water boil until it freezes. Okay, so there's ice in the boiling water. It's pretty interesting. So let's see, this point right here, this is the critical point. And that's the point beyond which there's no difference between a liquid and a gas. Beyond the critical point, no difference between liquid and gas exists. So it just becomes one phase, and it kind of extends kind of like that. So in this region here, that's where the you have what we call a supercritical fluid. And super just means above, so supercritical means it's above the critical point, and we just have a one phase there. There's no liquid, there's no gas, it's just a supercritical fluid. All right, now let's put a mark on this plot for 1 atmosphere. 1 atmosphere right there. Okay, let's take our ruler, and I'm going to extend this line, go out till I cross these other lines. Not a very good dotted line, but that's okay. Then I'm going to drop down to the x-axis. And we can read a temperature off of there. And I assume you all know what temperatures those are going to be. Right here, what happens when we cross from solid to liquid? When we go this way, well, it melts, right? We get melting. So that right there is 0 degrees Celsius. That's the normal melting point. And what about the other one? Well, when we go from a liquid to a gas, what happens here? We get vaporization. So this temperature here is 100 degrees Celsius. Not there, not there. Okay, that's the normal boiling point. We get those straight off a what did I call this thing? Phase diagram. All right. So one more thing I want to talk about on this phase diagram. Anybody like ice hockey, not very popular out here in California, but if you watch ice hockey a lot, you know probably that their skates are very, very sharp. And you may also know that really cold ice, really hard cold ice, is really pretty easy to walk on. I mean, it's definitely more slick than dirt, but you can walk on it. Why are those skates so sharp though? Well, imagine a 225-pound hockey player putting all of his weight on one little thin knife edge. So the ice is solid. It starts off right here, and when he puts all of his force on that little knife edge, the pressure increases. As the pressure increases, what happens? We go from a solid to a liquid. The act of that hockey player skating on the ice actually melts the ice right under his blade, reduces the friction, and allows him to skate faster. There's more than that, just that going on, but that is one of the things going on with an ice hockey skater. And the reason that happens, notice the slope of that line. Okay, I know our phase diagram is getting really messy, but notice the slope of this line. That's a negative slope. Negative slope means the solid is less dense than the liquid. Well, what does that mean? Solid is less dense? That means the ice floats. Your ice cubes float in water because the ice is less dense. Let's look at another phase diagram and see if that's the case. So here is a blank phase diagram, and we'll just go ahead and fill it in real quick. Okay, same kind of deal here. However, we have the triple point, critical point. Now let's start off right here. Let's just fill in all of our phases real quick. Solid, liquid, and gas. Oh, I'll tell you what this is for. This is for CO2. Okay, lots of different substances will have this type of phase diagram. Let's just say we start off right here, and it doesn't matter which temperature and pressure you pick. If it's in the solid phase for CO2, you go up, you're never going to liquefy. It's never going to melt. That's because solid CO2 is more dense than the liquid. If we drink CO2, liquid CO2, and we put a cube of solid CO2, the solid CO2 would sink. Solid CO2 is more dense. Is more dense than the liquid. And the steeper the slope, the closer to horizontal, the further from vertical, the larger the difference in densities there is. Because if you think about it, if we had just a perfectly vertical line, then the densities would be the same. Okay, but we don't. Oh, and the supercritical CO2. Anybody have any idea what that is good for? Well, if you ever drink decaf coffee, which you probably don't, but if you drink decaf coffee, it is decaffeinated with supercritical CO2. It used to be decaffeinated with things like dichloromethane and other organic solvents, but they're hard to get rid of, so your decaf coffee would have a little bit of residue of dichloromethane. Well, CO2, supercritical CO2, caffeine is hydrophobic. I'm sorry, it's nonpolar. So you can use the CO2, which is nonpolar, to extract the caffeine. Then you just return the coffee to room temperature and pressure. All the CO2 just evaporates away, and there is no residue left behind. Okay? And in case you don't drink decaf coffee, which I doubt you do, that's where all the caffeine for your energy drinks comes from, or for Coke, Pepsi, what have you. If there's caffeine in something that's not coffee or tea, it's been added from the extraction from coffee or tea. Okay, one more thing about phase diagrams. I just want to show you one. This is for carbon. And carbon is interesting. You'll notice that there are two solid phases, graphite and diamond. Okay. And excuse me. That's pretty common for complex phase diagrams. We kept them simple, but like I said, they can get really complex. We also have the liquid and the vapor like we would expect. But now, I want to save you some money in the future, okay? And I want to do that by explaining to you that diamonds aren't stable at room pressure, okay? So diamonds are formed at very high pressure. Now, if you remove that diamond from that high pressure and bring it down to atmospheric pressure, what's going to happen? It's going to turn into graphite spontaneously. And this is not a joke. It will. Every single diamond on every single ring is spontaneously turning into graphite. Okay? So when you buy your fiance a ring, buy her a graphite ring and tell her graphite is forever. Just don't tell her that it takes several thousand years for a diamond to turn into graphite. Anyway, that's it for chapter 12. Good luck on the exam.